Introduction to the binomial distribution. The binomial distribution is a fundamental concept in statistics that allows us to model the number of successes in a fixed number of independent trials. Each trial has two possible outcomes, success or failure. Key aspects. Probability of success. Defined for each trial. Fixed number of trials. A predetermined number of attempts is made. Applications. Useful in various fields such as finance, healthcare, and quality control for analyzing outcomes in yes/no scenarios. This presentation will explore the properties, applications, and formulas associated with the binomial distribution, providing a comprehensive understanding of its significance in statistical analysis. If we perform a series of independent trials, such that for each trial P is the probability of success and Q that of failure, then the probability of X successes in a series of n trials is given by n choose X, multiplied by P raised to X, multiplied by Q raised to the power of n minus X, where X takes any integer value from 0 to n. The probabilities of 0, 1, 2, 3, etc. up to n success is given by successive probabilities Q raised to n choose 1, P, Q raised to n minus 1, n choose 2, P squared, Q raised to n minus 2, etc. up to n choose X, P raised to X, Q raised to n minus X. The probability of the number of successes so obtained against a discrete variable X, assuming different values X sub I from 0 to n, constitutes a binomial distribution. In this slide, the mean of the binomial distribution is derived from the binomial equation for X successes out of n trials with a given probability P. The mean of any discrete distribution is derived using the expression for the expected value, which is mu equals summation X sub I equals 0 to n, X sub I, times f of X sub I. Substituting for f, X sub I, we get the expression shown in red, that is, summation I equals 0 to n, X sub I, times n choose C, X sub I, P raised n, Q raised to n minus X sub I. In the first column of the table, values of X sub I equals 0 to n, are given. In the second column, respective values of X sub I from the first column are substituted in the equation for f, X sub I, and simplified. In the third column, the products of X sub I and f, X sub I, are given. The summation of all the terms in the third column will give the value of the mean mu, which is shown in the next slides. This slide shows the summation of the terms obtained by substituting I equals 0 to n in the equation summation. I equals 0 to n, X sub I, times n choose C, X sub I, P raised n, Q raised to n minus X sub I. The terms are shown in red. In this slide the series is simplified term by term and the product, NP, is taken out. When NP is taken out, it can be seen then the series is the expansion of P plus Q, raised to n minus 1. Since P plus Q is equal to 1, the summation reduces to NP. In this slide, the variance of a discrete distribution defined as sigma squared equals to summation I equals 1 to n, f, X sub I minus mu squared is simplified as the expression sigma squared equals summation of f X sub I times X sub I squared minus mu squared. The derivation uses the identities sigma f X sub I equals 1, that is, the sum of all probabilities, and sigma f X sub I equals mu. In this slide and the following slides, the derivation of the variance of the binomial distribution is discussed. The identity mu equals NP is substituted in the equation for the variance, summation of f X sub I times X sub I squared minus mu squared, shown in red. The expansion of the expression, summation of f X sub I times X sub I squared, by substituting the values of X sub I for I equals 0 to n, results in a series as shown in blue. The combination expression in each term, such as n choose 1, n choose 2, etc., is expanded as shown in violet. Further simplifications, as shown in the box, such as 2 squared divided by 2 factorial is 2 divided by 1 factorial, and 3 squared, divided by 3 factorial, as 3 divided by 2 factorial, etc., are implemented. From the resulting series, NP is taken out as a common factor. The expanded and simplified series is shown in black. In this slide, from the expression for the variance, the term summation of f x sub I times x sub I squared is expanded by substituting the values of x sub I for I equals 0 to n in the expression. A closer look will show that the first series is the expansion of p plus q raised to n minus 1, and the second series, on factoring out, n minus 1 times p, is the expansion of p plus q raised to n minus 2. On simplification, we get the summation of f x sub I times x sub I squared, which reduces to np plus n squared p squared minus np squared. On substitution of the results previously obtained in the equation for variance, that is, sigma squared equals summation of f x sub I squared minus n squared p squared, we get np minus np squared. On simplification of np minus np squared, we get np times 1 minus p, which is npq. Numerical example 1. It has been claimed that in 60% of all solar heat installations, the utility bill is reduced by at least 1/3. Accordingly, what are the probabilities that the utility bill will be reduced by at least 1/3 in A. 4 of 5 installations, B. At least 4 of the 5 installations? Solution A. X equals 4, N equals 5, P equals 0.6, Q equals 0.4. The probability of 4 out of the 5 installations, substituting the values in the equation NCXP raised to X, Q raised to N minus X, we get P, 4 out of 5, equals to 0.2592. In continuation of the previous numerical problem, solution B, P, at least 4, equals P, 4 out of 5, plus P, 5 out of 5. Substituting in the equation for binomial probabilities, P, at least 4, equals 0.078 plus 0.2592 equals 0.337. Numerical example 2. Find the probability that in 5 tosses of a fair die, A3 appears A, at no time, B, at once, C, twice, D, 3 times and E, 4 times. Let the probability of 3 occurring be P. P equals 1/6, Q equals 5/6. The answers to 2A, 2B, and 2C can be obtained by directly substituting the values of N equals 5, X, P equals 1/6 and Q equals 5/6. The results are shown in the slide. Continuing from the previous slide, numerical example 2, the answers to 2C, 2D, and 2E are obtained by substituting the values N equals 5, X, P equals 1/6 and Q equals 5/6 in the equation for binomial probability. The answers are shown in the slide. Numerical example 3. If the probability that a man aged 60 will live to be 70 is 0.65, what is the probability that out of 10 men, now 60, at least 7 will live to be 70? P equals 0.65, N equals 10. Probability of at least 7 to live up to 70 equals probability of 7 men living up to 70, plus probability of 8 men living up to 70, plus probability of 9 men living up to 70, plus probability of 10 men living up to 70. P underscore, at least 7 live up to 70, equals 10 choose 7, times P to the 7th power, times Q cubed, plus 10 choose 8, times P to the 8th power, times Q squared, plus 10 choose 9, times P to the 9th power, times Q to the 1st power, plus 10 choose 10, times P to the 10th power, times Q to the 0 power. Normal approximation to the binomial distribution. If n is large and neither P nor Q is too close to 0, the binomial distribution can be approximated by a normal distribution with standardized variable given by z equals the quantity x minus np, divided by the square root of npq, where mu equals np, and sigma equals the square root of npq.